Good morning, iPad Geometry Initiative 2 students from OHS. This is your favoriteest teacher, Mr. Lane, teaching you a brand new geometry lesson today over section 3-4, which is over perpendicular lines. Today we'll be talking about different types of theorems and how to apply those that form perpendicular lines. Hopefully we kind of know the definition of perpendicular lines already. Hey, I got a secret for you this morning though. Don't tell anybody, but you're my favorite student. Yes, I'm talking to you. You are my favorite student. But anyways, in your notes right now, you need to have that section title, 3-4 perpendicular lines. You can read through the objective, read through the why on your own time there, and answer the number 5 in your notes now. Some of you guys are doing an excellent job of that. Some of you guys still need a little bit of work. If you don't know perpendicular lines, by the way, let's take a look at those just a second here. Perpendicular lines, remember we've been talking about parallel lines, which are two lines that do not intersect, that's on the same plane. Well, now perpendicular lines, we're going to have them almost the opposite of that. They are going to intersect, but not only are they going to intersect so that you know they're on the same plane, they're going to form a right angle. So hopefully you already know perpendiculars form a right angle. That will help you out throughout the lesson today. Let's take a look at maybe the first couple of things. I think we want to talk about a perpendicular bisector. I think we've already done this of a segment, but the tools are pretty cool here. So I'm going to take it and we're going to walk through a segment bisector one more time with you. Remember that it's a line perpendicular to the segment at the segment's midpoint. So it's going to create a 90-degree angle cutting through the segment's midpoint. So I'm going to put the end of the compass right at one of the endpoints of the segment, and then I'm going to go ahead and mark an arc just like that, and then I'm going to put the compass on the other endpoint of the segment, and I'm going to turn this a little bit. Actually, I'm just going to mark it all the way across there. Okay. Now, all we have to do is mark a segment or a line or a ray that cuts right through those two intersection points. This one right here, which we could call A, this one right here, which we could call B, and any segment, line, ray that cuts through there is going to be the perpendicular bisector of that segment. So notice that when I put that in through there, it forms a just a touch. It forms a right angle right there at the intersection point. So remember the red little boxes in the diagrams just marks that right angle for us. So that is a perpendicular bisector. And what that means is this segment here, let's call this C, let's call the intersection point here D, and let's call this E. Well, we could say that CD is congruent to segment DE. So that would be true given the perpendicular bisector. And I think we've looked at that before in the past. Alright, so what type of problems are they going to ask us? Well, they're going to ask us to work problems such as this, that we're trying to find the shortest distance and write inequalities about the shortest distance. So as we hopefully know, that the shortest distance from a point to a line is the length of the perpendicular segment from the point to the line. And that's kind of common sense in that the fact that here's my line, here's my point. Well, if I was to, I could draw a couple of different lines from this point to that segment, and they would be straight lines. So people that say, oh, the shortest distance between a point or two distances is a straight line, well, there's several different straight lines that we could look at. So if you notice, the shortest one here is going to be that perpendicular segment to the line. So this green dotted line is going to be a lot shorter than that blue one or the red one. So the shortest distance is a straight line, but more importantly, it's the perpendicular line between that point and that segment that's going to be the shortest. So if we look over here at the diagram, I think it's just wanting us to name the shortest segment from A to line BC real quick. So here's our point A, and then our segment BC is right down here, or line BC is right down here. So we know then that the shortest segment is going to be that perpendicular segment. So segment AP is going to be that shortest segment. So that length 12 is going to be the shortest distance. This AC is going to be longer than it, and this AB is going to be longer than that distance of 12. So then it's going to go on and ask us, write and solve an inequality for x. All right, well, let's just compare the two distances here. We know that the length AP is the shortest distance, so it's got to be smaller than, remember the alligator always eats the bigger segment, or the bigger mill or number, so AC has got to be bigger than that shortest distance, which is AP. So now if I substitute in here real quick, I could say that 12 would have to be less than that other distance, which is not the perpendicular segment, which is x minus 8. So that has to be true. So now all I have to do, I think, is solve this for x. That's what they mean by write it. To solve for it, if x is being subtracted 8, I just need to do the opposite, which is add 8. So it looks like I'll get 20 on this side is less than x over here because the 8's will add out. And then a lot of times we'll just rewrite it with the x on the left. Notice that the alligator is still eating the x, so when I rewrite it, that alligator, and if you need to draw in teeth to help you out, that alligator has to still be eating the x. So x would have to be greater than 20, for this inequality to be true. Quick reminder, if this would have been, let's say that segment would have been 8 minus x, I still would have set it up the same way as in 12 is less than, that should be 8 minus x. So let's rewrite. 12 is less than 8 minus x, and then I would have to subtract the 8 to solve in that situation, which would have gave me 4 is less than, that would have added out. Now I would have had negative x setting right here. Well, that's negative 1 times x, so the opposite would be to divide by that negative 1. And if you remember, any time that we multiply or divide by a negative 1, that sign is going to flip directions. So now it's going to flip the other direction. I'd be left with x and negative 4 over here. And then notice that the alligator is eating the negative 4, so when I rewrite with x on the left-hand side, now the alligator has to be eating the negative 4. So that's how we can rewrite it. So a little review on inequalities right there. Let's see what's next. Regular geometry students would be doing 2, 3, 6, and 7 at this point. iPad geometry class, your problems are always at the end. So I think we have some theorems. I would encourage you to write these in your notes. I'll try and draw a little diagram to help us out here a little bit, as there's only one of them that actually has a name to it. So the first one here says, if two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. Alright, so what does that mean? Well, let's draw a little diagram to help you out a little bit. Let's try and make a straight line here. And let's see, it says something about perpendicular, so I'm going to try and draw a little segment perpendicular here. And then it says that those two would be congruent. Alright, let's reread it one more time. If two intersecting lines form a linear pair, so this line and this line are my intersecting lines. They intersect right here at this point A. They form a linear pair of congruent angles. So linear pair means a straight line. I just marked the one arc, which would say that these two are congruent. Then those lines must be perpendicular. Well, if this is angle 1 and this is angle 2, if the measure of angle 1 plus the measure of angle 2 equals the 180, and they have to be the same measurement because they're congruent, then the only two things I could add together to equal that 180 would be the 90-degree angles. So that would make sure that they would be perpendicular then. Alright, perpendicular transversal theorem is in a plane. If a transversal is perpendicular to one of the two parallel lines, then it is perpendicular to the other line also. So let's see if we can get a drawing of that up here. So let's see. Here's my plane, here's my two lines, and I've got to have a perpendicular to those two parallel lines. Well, in this, if this angle right here was perpendicular so that I'd have one of them, if these two are parallel, then this would also have to be perpendicular. If we look at what type of angles those just appear to be corresponding angles. So we know that if these two lines are parallel cut by this transversal, then the corresponding angles have to be congruent. Well, if one of them is a 90-degree angle, then the other one would have to be a 90-degree angle. Okay? So now we have one last theorem here. It says if two coplanar lines are perpendicular to the same line, then the two lines are parallel to each other. So let's take a look at that one real quick. Alright, so I'm going to get me two coplanar lines, and then I'm going to get a transversal right here, and it's saying that if these two lines right here, like L and M, are perpendicular to the same transversal T, then that these two lines would have to be parallel. And that would make sense because 90-degree angles are congruent, or all 90-degree angles are congruent. So these would again be corresponding angles. So the converse of the corresponding angles postulate would tell me then that line L and line M would have to be parallel. So it kind of builds off of the last sections in that aspect of the lesson. Alright, so now we're going to talk about some proofs here. I've got a diagram right up here. I've got a two-column proof set up right down here with some statements and some reasons. We're supposed to write a two-column proof given that R and S are parallel, so I always like to mark that information if it's not already marked in my diagram. And then that angles 1 and angles 2 are congruent. And I'm going to go ahead and out here label what type of angles those are. So those are on the inside of the lines R and S, and on opposite sides of the transversal T. So those would be alternate interior angles. So then I'm supposed to prove that R is perpendicular to T. So let's try and do that real quick. I'm going to go ahead and just start with the given information. Always a good place to start here. So my number 1 is going to be R is parallel with S, and my reason for that is going to be given. My number 2 here, I'm going to go ahead and list that angle 1 is congruent to angle 2, and that is also given. I just noticed in the proof here that I've got angles 1 and angles 3 labeled on the wrong angles. So it looks like I only got about a minute and a half. We're going to try and fix this real quick and get this straightened out. So again, I'm just going to mark that angle 1 and angle 2 are congruent, and that I have those parallel, which I've already marked. Now angles 1 and 2 aren't any special type of angle, so I'm going to mislabel that. But I am going to label that 3 and 2 would be corresponding angles, which I know are going to be congruent. And actually, that's the next thing I'm going to write down on my proof, that by the corresponding angles postulate, angle 2 would have to be congruent with angle 3. So what's that going to give me that helps me or benefits me out? Well, if I got 1 is congruent to 2 and 2 is congruent to 3, then I can say that angle 1 is congruent to angle 3 by either substitution or probably more the transitive property of equality, or of congruence actually. Alright. So then I need to wrap this up. I only need one more thing here, which is R is perpendicular with T, and that reason is going to be that two intersecting lines form linear pairs of congruent angles, then they are perpendicular lines. So it's one of the theorems from the last page. So you can abbreviate